Just like the other tests, the Unit 4 test, you will have 2 hours. We will only take the 1 hour in class, so technically the 45 minutes or whatever. So you will have like an hour and 15 minutes outside of class you can arrange to finish that up. And yes, you will be able to use your notes and your book. So the last thing we need to wrap up today is organizing data into graphs. We've looked at graphing relationships and equations and doing different sorts of algebra-based graphs. Let's look at data-based graphs. And really, to organize data, we have to go through that same intermediate step that we did when we were graphing algebraic relationships. So when we had that y equals 3x minus 1, before we learned the shortcut for graphing lines, we did a table where we picked values for x. We might have done -2, 0, and +2. And we calculated what y had to be. So if x is -2, y would be -7. That's just 3 times -2 is -6 minus 1. If x was 0, 3 times 0 is 0, minus 1 is -1. And if x was 2, 3 times 2 is 6, minus 1 is 5. And then we just plotted those points on the graph. So -2, -1, 2, 3, 4, 5, 6, 7, 0, -1, and 2, 5. And so we plotted those points, and that allowed us to make the graph. Well, with our organizing data and graphing data, we're going to have to go through a similar intermediate step. Rather than starting with an equation, though, we're going to start with raw data. So raw data might take a couple of different forms. One form it might take would be categorical data. Categorical data involves basically data that puts people into categories. Just a half a step back, maybe. Data is about asking a question. And the answer to that question is our data. And that data can take a couple of different forms. One form it could take is categorical. And that categorical data, as we said, puts you into a category. We'll clarify that a little bit more as we look at specific data. The other type of data would be numerical. Numerical data, the answer to that question is a number. And there's a couple of types of numerical data that we'll cover. So for now, let's get back to that categorical data. Categorical data can take a couple different forms, but it always puts you into a category. One might be, do you support, maybe there's a local proposed ordinance, Proposition X. Well, your answer to that is going to be either yes or no. And those put you into a category. The category of those that favor the proposition or the ones that don't favor that proposition. We might have favorite color. So if you're asked your favorite color, whatever color you respond or you choose puts you into a category of the group of people that like that color or that prefer that color. So let's do that favorite color. And then we're going to offer only 3 choices here. So we're going to offer blue, red, and green. So let's say the question is, of these 3 colors, primary light colors, what's your preference? Which one do you prefer? So I'm just going to list off some data. I'm going to list B, R, and G just for short. And let's say we've asked people and we were going to list their responses. Let's say we have red, blue, red, red, green, blue, green, green, blue, red. Let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Blue, blue, green, blue, red. Let's see. So there's 15. Let's do one more row. Let's see what we've got. Red, red, green, red, blue, green, 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 red. Let's see what I've got. Green, blue, red, blue, blue, green. Now, looking at that, there's 30 responses listed there. Can anybody look at that and tell me what color is picked the most often? Well, with 30 responses, that's tough to do. The human brain, the psychology tells us the human brain can only really take in between 7 and 13 things at once. If you try to visualize more than that, some things fade off. So as you're looking at this, you would only be seeing part of it at any given moment. So you might focus here and see this section. Well, if I'm looking at that section, boy, it sure seems apparent that red would be the most popular color. If I looked at this section right here, boy, it sure seems apparent that green would be the most popular color. Or if I was looking down here, my mind would probably latch onto the blue as being the most popular color. So just looking at the raw data, it can be very difficult to figure out which one is the most popular. So our first stage in organizing this data so that we can go to a graph, similar to with the equations, is to create something called a frequency table. In the frequency table, list the categories. In this case, it's favorite color. So we're just going to say color is what that category is going to be. And then it would be frequency, telling us how often each color was selected. And that's all that would be in that frequency table. So let's go blue, red, and green. Now, when I'm constructing this, I usually add an extra column that's just kind of a working column that helps me create my table. If I were presenting this, this middle column that I'm putting in here would not be there. I'm just going to call it the tally column. And all that's for is to help me tally up the responses. And here's what here's how I'm going to do that. I'm going to go red, blue, red, red. So I've got red, blue, oops, red, blue, red, red. Green, blue, green, green. So green, blue, green, green. Blue, red, blue, blue. Blue, red, blue, blue. Green, blue, red. So green, blue, red. Red, red, green, red. Red, red, green, red. Blue, green, green, green. Blue, green, green, green. Red, green, blue, red. Red, green, blue, red. Blue, blue, green. Blue, blue, green. You can see from those tallies that each of them occurred exactly 10 times. So looking at the raw data, most of you probably would never have guessed that they all occurred exactly the same number of times. So that's one of the purposes of organizing the data, is to make that possible. Now here, with only a few colors, only 3 choices, it would be pretty easy to look at this table and say, now the numbers are all the same, but if they were different, it'd be pretty easy to look at this table and say which one happened the most often and which one was the least often, with only 3. But if there were more choices, that would be a little more difficult. So let me just do a frequency table here. I'm not going to show you the raw data. This is after we've already organized it in the frequency table. Notice there is no tally column in this frequency table because it's finished. Up here, before I presented this, I would take this tally column out and I would just have that two columns with the color and frequency. So let's just say we've got choices A, B, C, D, E, F, and G here. And our frequencies, we got 7, 12, 9, 11. So what's that come up to? 6, 3, and 2. So looking at these, there are only 7 choices here, but still it's kind of tricky to pick out which one happens the most and least often. There's enough of them that you got to really kind of sort through them. So the next step to make it a little quicker to recognize those things would be to create some sort of a graph. The first type of graph we might create would be a bar graph. Now I'm going to kind of breeze through these graphs because most of you have seen these graphs before. Now a bar graph can be done one of two ways. I can put my categories on the left side, like that, and then number on the bottom here and run my bars that direction. Or I can put my categories along the bottom and I can run my numbers up the left side. Now, statistically, generally we prefer having what's called a vertical bar graph, which means the bars do go up and down. Now, as I number this here, my frequency, I have to make sure I go up to at least as far as the largest number. I look through here and I see the largest number looks to be 12. So I have to make sure I go at least to 12 on my number scale here. Now here I was able to number by ones, but if you had larger frequencies, you don't have to number by ones. I'll show you an example of that in a little bit. So here, letter A had a frequency of 7, so I'm going to draw a bar up to 7, over and down. B had a frequency of 12, so I draw a bar up to 12, over and down. C had a frequency of 9, so I go up to 9. D was 11, so I go up to 11, over and down. E was 6. F was 3. And G was 2. So a couple of things to point out. Because this is categorical data, there is always space between the bars. Because the categories theoretically could go in any order. There isn't necessarily, in this case, there were A, B, C, A through G, so there is a logical order, but there isn't necessarily a connection or a flow from one to the other. Second thing you'll note, I didn't do a great job of it, but I tried to be careful to make sure that all the bars were exactly the same width. Wasn't terribly consistent, but I stayed pretty close. The reason for that is it could be very deceiving. I might, rather than keeping them the same like that, maybe I would do B like that and D like that. So if I remove the brown, now when I look at this, even though B is taller, the width on D psychologically messes with your mind a little bit, making you think that, well, maybe D is larger. Even though it is shorter, the width gives you that second dimension, messes with your psychological perception. And there are a lot of psychological things that can be done with these graphs. For example, let's do this. let's say that we're comparing three companies, A, B, and C. And we want to show their difference in sales. And this is in thousands of dollars per month. So I've got my number 200, 210, 220 up through there. And A looks like this. B like that. And C like that. Now, if you look at this, you look at B and you think, wow, B really dominated this. It's way larger than the others. I mean, it's almost twice as tall as A, and it's more than twice as tall as C. So you look like, well, B really did much better than those other businesses. But if you look at the numbers here, you realize this little symbol here means that there's a break in the scale, that we didn't start at 0 and number continuously on up through. Now, there are good reasons why we would do that, but here you can see it can be very deceptive. So when reading a bar graph, you have to be careful. This looks like B is much larger than the others, but if I drew it without that break in the scale, it would look something like this. Oops. Let me try that a little bit better. A is a little over 200, B about 220, and C is just a little over 200. So you can see B is still definitely larger. There's very little difference between A and C. I mean, B is definitely larger, but not really by much. Now, one of the major weaknesses in this graph is, let's say I wanted to know what were the sales for A. Well, I follow this over, and it's really tough to estimate. I know this is 250 up here, but is that 210, 205, whatever? I follow C over. I know that's between 200 and whatever A is, but finding that exact number is tough to do. Same with B. I can see it's less than halfway up. It's less than 225, but is it 220? Where does it sit? So one of the weaknesses of any graph is finding exact numbers. If I want the exact numbers, that's where I would go back up to a table like this and look them up in a table. That gives me the exact numbers. So over here, I still can't necessarily find the exact numbers, but I can tell at least that company A is 207 to 208, somewhere in there. And that company B is really close to 220. And C, probably 205, 206. So you can come a little bit closer by breaking that scale. You still can't get exact numbers. So like I said, there are reasons to do this break in the scale so you can get a little bit better idea of the numbers, but it is deceiving. One of the strengths of the graph, the weakness, of course, is you can't get exact numbers. One of the strengths is finding the largest or smallest. In either of these graphs, we can see very clearly that B is the largest because it's the tallest. This one is pretty easy to see that C is the smallest. Here, you'd have to look a little closer, but you can still pretty well pick out that C is the smallest. Second strength would be to compare. Now, there's only 3 items here, so there's not a lot of comparisons. Let's say I asked you, which is larger, A or C? Well, you look at it and see, well, A is a taller bar, so A is larger. So you can get those comparisons really quickly. But if I wanted to know how much larger is A than C, well, then we're talking about those exact numbers again. And that's where we'd want to go back to a table to get those exact numbers. So that's the bar graph. Let's look at some other types of graphs we might want to look at. So let's look at that favorite color. Again, I'm going to put some different numbers in there so they're not all 10. Now you note I had green there. I redid that. That's another psychological thing. I'm putting it in black so that the lettering is not any of the three colors. If I had done this in green, even though green may have the smaller number, seeing the color green draws your mind to start thinking green. So again, another one of those little psychological tidbits. So let's say we have 12 that choose red, um, 8 that choose blue, and 10 that choose green. Well, another graph that we might construct is a circle graph or a pie chart. Circle graph or a pie chart normally goes off of percents. So if I look at this here, one of the first things I would have to do with my data is convert it into percents. That's something called a relative or percent frequency. So to do that, the first step would be to find the total. So I add those all up, I get a total of 30. So that 30 is what I'm going to use to calculate my percent. The relative frequency or percent frequency is the percent of total. So 12 would be 12 out of 30, which is 0.4 or 40%. Technically, the 0.4 would be the relative frequency, and the 40% would be the percent frequency. 8 would be 8 out of 30, which would be 0.267, so 26.7%. And 10 would be 10 out of 30, which is 0.333 or 33.3%. Now, if we added these up, of course, the relative frequency should add up to be really close to 1.00. They might be a little higher, like 1.01 or 0.99, because there's going to be some round off here. Here, our round off, we happen to have one that rounded up and one that rounded down, so it's going to cancel out. But it won't always do that. You may have, like I said, 1.02 even, or 0.98 because of that round off. And of course, the percent should add up to 100%. Now, 20 years ago, or maybe even a little bit more than that, we would have taken these percents and we would have taken 360 degrees, which is a full circle, and we would have found, what percent or how many degrees is that percent out of 360. And we would have then used a protractor to measure out that many degrees on our circle. Well, now if we wanted to get that perfect, there's all sorts of computer programs, Excel being one of them, that'll make that circle graph perfect for us, so we don't need to worry about it. So what we're going to do is we're just going to use some approximation here. And we're going to go off the percents. We know that half of the circle would be 50%. A quarter of the circle would be half that, or about 25%. Half of that would be 12.5%. So we use that for what we have here. Well, the first one I noticed that's close to that, the blue is 26.7%. That is just slightly larger than 25%. So that's our blue. The green is 33.3%. That's exactly 1/3 of a circle. If I put that would be 25%. Half would be 37.5%. 25 plus 12.5. So I know it's a little less than that. So somewhere in there. So divide up. That is going to be 33%. That is the green. And of course, the rest of this is going to be the red. And for our purposes, that is good enough as a circle graph or a pie graph. Now we might be given numbers in here that green was 10, blue is 8, and red is 12. some things we might need to be able to read off of a graph like that. And we might need to be able to go the other way and find the percents. So let's say we're given a graph. Let's say we're given a breakdown of grades. So let's say the students who got an A, there were 9 of them who had an A. Let's say students who had a B for their grade, there were 16. And students with a C for their grade, well, let's say there were, what am I saying? Now let's put that at 15. So I'm going to open this up a little bit more. Something like that. So now I want to ask what percent had a B, earned a B. Well, I need to find the total again. So I'm just going to add up those 3 frequencies. 9 plus 16 plus 15 adds up to 40 is my total. And that's just calculating a percent. B was 16 out of 40. How many would that be out of 100? 100 times 16 divided by 40 is going to give us 40%. So 40% of the students had B's in that class. We might also look at it from the other direction. We might say, out of 200 students, pretend that looks like a circle. We had A was 21%. B, let's say, is 34%. C is 39%. And what's that leave us with? D would be 6%. We want to know how many earned a C. So now we have to go the other direction. We have the percent. C, I see didn't show up in there. C was 39%, so that's 39 over 100. How many is that out of the total of 200 students? So we would cross, multiply, and divide. There were 78 students with C's. Okay, so our final type of data graph that we want to talk about is a line graph. A line graph is a little bit different than the ones we've seen before. The last few that we've looked at, they have represented a single value, or sorry, they've represented different possibilities for a variable at a single point in time. A line graph represents only one item, but at different points in time. It's referred to as a time series. For example, we might do cost per credit at WITC. So let's do 2010, 2011, 2012, 2013, 2014. And we'll do 2015. For the year and cost per credit. So let's say in 2010, the cost per credit was $138. In 2011, it jumped up to $152. 2012, $154. 2013, some changes in funding, it dropped to $147. 2014, $149. And in 2015, $155. So again, we're going to make a graph. When time is involved, time is almost always on the horizontal axis. So we're going to 2010, 2011, 2012, 2013, 2014, and 2015. Now here, because we are comparing, I am going to cut off my axis. So that little symbol means my axis does not continuously go from 0 on up. The smallest number I'm going to represent is 138. So let's start out at 130, 135, 140, 145, 150, 155. So that's the largest number I need to represent is the 155. So in 2010, we were at 138, somewhere in there. 2011, we jumped to 152. 2012, 154. 2013, oops, I gotta move that over just a touch. There. 2013, we dropped to 147. 2014, 149. In 2015, back up to 155. So we connect these. Okay, now a couple of things. One mistake that's very common is a lot of people want to connect this like that down to the origin of the graph. Don't do that because that's not true. There was never a point here where that cost was 0. So don't resist that temptation. Now the other thing is the biggest strengths of the line graph is that the slope of our line is a change. So we can very quickly look at this and see when was the cost of tuition increasing, when was it decreasing. Well, as we look at this, we can see there's only one point where it was decreasing, and that's right here from 2012 to 2013. That's the only place where the line slopes down. All of the other years, it's increasing. The other thing we can do is we can see when was it increasing or decreasing, the fastest or slowest. The fastest increasing was right here because that's where the line is the steepest. Slowest, don't cross my L's. Slowest increasing was right here because that's where that line is the shallowest. So you can see, and actually it's probably tied, these two points are actually the same slope. So both of those had only increased $2 those years. So we can see those slopes being the same, it was increasing the same rate on both of those, and they were tied for the slowest rate of increase. So that line graph shows us that change over time. Okay, so we do have a little bit of time left. I wanted to make sure we got through the types of graph first. I want to go back now to that data, the histograms and the frequency tables. We did categorical data before. Now I want to do an example of numerical data. Well, numerical data can take two forms. It can be what's called discrete or continuous. Discrete simply means countable. How many classes are you taking right now? How many cars do you own? How many siblings do you have? Those are things you would count. How many books are in your backpack? Continuous are things that are measured. This would be like, how tall are you? What's your height? What's your weight? How long does it take you to do a certain thing? Time is continuous. The technical definition of continuous is no matter how close two numbers are, you can find a number in between them. Discrete, there are numbers that are not the same without things in between them. The big argument comes up usually, what is money? Is money discrete or continuous? Well, If you have $3.27 and I have $3.28, is it possible for somebody to have a number in between there? Well, theoretically it is, but in reality it's not. So money actually does get put into discrete because there's a spot where you have two numbers that are different, but you can't get a value in between them. Discrete money technically is counting your pennies. Time is another argument. Time, however, is limited only by rounding. So you might round off the time, in track, they'll round off your time to the nearest hundredth of a second. Well, so it is possible for two people to have exactly the same time, but that only is true because of we chose to round to that. If you could go to as many decimal places as you wanted to, and eventually there would be a slight difference. So time goes under continuous because it is always possible to find values in between. So if we were doing a frequency table with discrete data, we might have what is your, let's say, how many classes are you taking right now? And let's look at WITC students so you get a little bit more of a range. High school, they pretty much tell you you have to have at least this many classes. You may get one or two study halls or free periods, but you're pretty limited in your classes. So let's say if you're taking 0 classes, you're not really a student. So let's say we've got 1, 2, 3, 4, 5, and 6. Let's say nobody took more than 6 classes. Say that of those we surveyed, there were 7 people that had 1 class, 11 people with 2, 15 with 3, 31 with 4, 20 with 5, and 9 that took 6 classes. So there is our frequency table, and we can go ahead and make a bar graph off of that. 1, 2, 3, blah, 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 and make those bars. Now, one thing that would be different in our bar graph, I'm going to go ahead and draw this out a little bit better. Let's do 10, 20, 30, and on up. One thing that would be different in our bar graph here, 1 is 7, 2 is 11, 3 would be 15, 4 is 31, 5 would be 20. Oops, get back up there. And 6 would be 9. You'll notice, unlike the categorical data where those bars had space between them, here the bars are tight together. The reason for that is there is a logical connection from 1 to 2 and 2 to 3. So when we do numerical data, we tend to put the bars tight together. So discrete, that's really the only difference between the discrete data and the categorical data. For continuous, however, let's say we wanted to do height and frequency. Well, let's say we're measuring the nearest tenth of an inch. Well, even if we had a large group of maybe 50 people that we were measuring height, going to the nearest tenth of an inch, we'd be lucky if we had more than 1 or 2 that were really the same height. Everybody would be a slightly different height, so we can't list out the numbers individually. So for continuous data, we usually put ranges in here instead of individual numbers. So we might have 60 to 63.9 inches, and 64 to 67.9 inches, and 68 to 71.9 inches, and 72 to 75.9 inches. And then list our frequencies. So there might be 7 people in the 60 to 63.9, 21 in the 64 to 67.9, 28 in the 68 to 71.9, and 11 in the 72 to 75.9. So you would get your same breakdown there. Okay, that pretty much is our time for the day. So some homework on these. For data graphs, organizing data, page 321, 1 through 7. Do all those just looking at the graphs. And then page 326 through 330, again, analyzing those graphs 1 through 10. And remember, Wednesday is our Unit 4 test. So all of our stuff on graphing lines and parabolas, variation, all that stuff will be on that test. Anybody have any questions? Okay, well, you guys have a great day, and we'll see you on Wednesday.